love to tell you some things that we've been doing for the past few years on simulations of the first generations of stars, black holes, and galaxies. So basically the first billion years in the universe. And this is work done with several of my collaborators. I want to just point out two of my students. They're both second years, Danielle Skinner and Corey Brumwell-Smith, who was here last summer as part of the summer program here. Also, my collaborators from Dublin, Turlock Downs, John Reagan, Mike Norman, Brenton Smith in San Diego. He has moved to Edinburgh now, Brian O'Shea, and Yuya Sakurai. Okay, so an outline of this next 50 minutes or so, I want to start out just on the first generations of stars, these metal-free stars and their properties and their actual effects on the next generation of structure that forms, or these first generations of galaxies, and what are their physical properties and how do they affect large-scale structure and affect reionization. And because that's important to understand, because these are the building blocks of all galaxies that we see today, and all of the galaxies that we see in the ultra-deep fields and the frontier fields. And then once we go over these, I'm going to highlight some results on two simulation suites. One that was older, that's kind of set the scene for these bigger simulations, the Renaissance simulations, which we've been analyzing for the past 5 years or so. But basically, I want to look at like what are the properties of these dwarf galaxies, young galaxies, prior or during the epoch of reionization, and how do they contribute to reionization, specifically like how much UV light gets out of the galaxy, because it's a very hard problem. Also luminosity functions of these galaxies. And finally, I'll end with some recent work that we've done on massive black hole formation, these sea black holes I briefly touched upon in the galaxy formation group meeting today. Okay, so everyone starts out with the cosmic timeline. I'll start with my own. So here's, this whole talk will focus on the first billion years, how we have these first generations of stars forming, and these metal-free stars, they're massive, they're thought to be massive, and they'll form their individual cosmological H2 regions. And as structure forms, it transitions to the first galaxies, they form their H2 regions, grow bigger, the Swiss cheese gets more and more and more, you get overlap of these ionized regions, and you transition to fully ionized around redshift 6 or so. But we're mostly interested in this time here, right? So because I think that those galaxies form in those first billion years, and they continue to grow, and we're interested in these tiny spots, those most distant, those most faint galaxies, those building blocks of all galaxies that we see today. As we look in the ultra deep field or extreme deep field, we see all different shapes and sizes and colors of galaxies, and we all want to know, how did these form? And what are their evolutionary sequences? What are their stellar populations, star formation histories, their black holes, their central black holes, and so on. And the list goes on and on and on. And what our group and my collaborators are interested in are these most distant objects. So we have to tease out information about this blob here, right? This is one of the most distant galaxies that was observed. I think it was who did it. I was in Boeing's group, I can't remember, but it was redshift 10, but this is like 4 pixels across. We want to know what its star formation history is, when did it start forming stars, the stellar mass, and so on. So we build models of galaxies that actually that we can actually make mock observations of and compare it with these observations. But to begin with, to actually simulate these first galaxies, I think it's extremely important to understand the complete star formation history of these first galaxies, and that begins with the first stars, the first generations of stars in the universe. So we can ask simple questions to ourselves, right? So we can look around us and just ask a simple question: why do all stars contain metals? I like history, and when I was a PhD student, I went on a literature search and found the first instance of the first mention of population 3 stars. So this was Martin, Schwarzschild, and Spitzer back in 1953. But they saw that, they saw 3 things. They saw a very low abundance of metals in the earliest pop 2 stars, high frequency of white dwarfs, and red and dead galaxies. But they came to a conclusion, I found this amazing, way back then, is that the original stellar population 2 stars contains a large number of relatively massive stars. So even back then they were saying, oh, there are no metal-free stars around us, so they have to be all massive, but back in 1953. Okay, the second question that you can ask is, right, if we look in the Milky Way, most cooling happens through molecular hydrogen cooling on dust grains. But if you have no metals, how does the gas cool to form stars in the early universe when we just have hydrogen and helium? Is that in the 60s, some chemical networks were studied, and it was discovered that you can actually form molecular hydrogen in the gas phase, not on dust grains, through this intermediate phase forming H-, through this catalyst of you need free electrons to undergo this intermediate stage to actually form H2, and that's a very slow process when you consider it happening in 3D space in the gas instead of on a 2D surface on a dust grain, right? So H2 formation is slow in the gas phase, so that will limit cooling. So that's something different than present-day star formation. And the third thing, simple question, but has complex answers, is when and where do the first stars form? So in the mid-80s, Hugh Cashman and Martin Rees, right, they came to the conclusion that these first stars, they form in rare cosmological peaks around 1 million solar masses at very high redshift, 20 to 30, and also this minimum mass will be redshift dependent. Right, so, but all this work in the 20th century set the theoretical framework for cosmological simulations, or simulations in general, of the first star. So there are two independent groups that looked at this around the turn of the century, led by Volker Braun and Tom Abel. But what they found was that the gas cooled a few hundred Kelvin. So that's extremely warm compared to present-day star formation, which goes down to 10 Kelvin. But that sets the gene mass of the molecular cloud to around 1,000 solar masses. So at the time, they thought, and they saw in the simulations, that you had no fragmentation into low-mass objects. And this pointed toward, we had very massive stars, tens of, they had this range of 30 to 300 solar masses, right? And this is one beautiful rendering from Tom Abel that, these are density isocontours where you just have this monolithic collapse into a single massive object. But as time went on, people start adding more and more complex chemical models and higher resolution and sync particles into the simulation. They start to see fragmentation in the next decade. So there are many people that worked on this. This is my former group mates, Matthew Turk, also Thomas Greif worked on this, and Shingo Hirano. But this is a similar rendering where this is a wide binary forming. So you had 10 and 6 solar mass cores forming, and they're accreting at a pretty rapid rate. And this field of view is of 2000 AU. Right? And they can form in clusters now. Now more and more simulations have been done, and they're still they're thought to be massive, tens of solar masses. And because they're massive, and now multiple systems you have some multiplicity happening in these systems, you can have binaries. You can think of binaries forming, and high mass expert binaries might be possible in the early universe. And they still form in these small dark matter halos around 10 million solar masses or below. But the thing is, people are all looking for what is an IMF, or initial mass function. So it's pointing towards still top heavy, but its exact shape is unclear. So that was on a large scale, 2,000 AU across, fragmentation. Still looking at the first stars, and now Thomas Greif, he looked at disk fragmentation, so small scale fragmentation. Each row is a different halo, and left to right in time. But you can see that he evolved it for 10 years, and it took 3 months of computational time to do 10 years of evolution. But yeah, it's crazy. But you can see that the other simulations, they stopped. We went back to this one. You formed the first object here, and they stopped saying you have a massive star. But if you continue this simulation, say that's the starting point, and you see the disk forming around all that high angular momentum material forming around it, forming the disk, and then you can become two-brain unstable, start forming these clumps. And half of what he found, or they found, half of those clumps, they merged into the central object, and half of them went on to higher energy orbits and could become low-mass stars. So this is similar to present-day massive star formation, and also planet formation, right? Not exactly, but you still get some fragmentation in these disks. Okay, and also, all right, this is some work done by one of my graduate students, Danielle Skinner, looking at how many of these population 3 stars form in each halo, and you get a wide range of multiplicity in these halos. So this is just showing for a given halo mass how many pop 3 stars form in each halo. But around like you have a median of 4 forming in each halo, so we're no longer in like the paradigm where you have a single pop 3 star per halo, but you have like a handful of pop 3 stars. Where I think it's this 18% of halos that form population 3 stars contain a single star, but it's more common to have binaries or a system of population 3 stars all the way up to like 16. So and also we can look, I mean we have the number of stars, but when you start folding in, we have to assume an IMF, right, to go forward on this, to actually look at the effects of radiative feedback and supernova feedback. But if we look at the mass of population 3 stars per halo, it's still around 100 solar masses, but they're distributed in like 4 or 5 stars themselves. And also you can look at some star formation efficiency. And so that's just stellar mass over gas mass, and it's in between like 0.1% and 0.01%. So it's much less efficient than like present-day star formation. Okay, so another hard thing to do, like with massive star formation in general, is like when do these protostars actually stop accreting, right? What I've shown so far are just like pre-stellar gas, or not even accretion, right? Pre-stellar gas dynamics to a central point. But once you form that protostar, and once it starts radiating in the UV and the optical and infrared, how does that limit accretion? And this is a problem for present-day star formation and metal-free star formation, right? When do these stars stop accreting? This is some seminal work by Hosokawa-san in 2011 and 2016, where they actually looked at when these stars stopped accreting. So without any radiative feedback, this star that they're showing here just keeps on accreting. So over 60,000 years, it's still growing. It's gotten up to 150 solar masses. But when they include ionizing and dissociating dissociates H2 feedback, radiation feedback, it kind of limits it to around 60 or 70 solar masses. So it limits that, but you have to go by case. This is one case. And this is just a visualization from their paper where it's showing temperature and density, and you get these biconical H2 regions that the radiation comes out. Here's the disk-like structure that forms, but most of the radiation comes out through the poles, and eventually over time, you shut off accretion on the central source. Okay, so, but that's one, these are two cases. This is from the 2011 paper. This is axisymmetric 2D problem, 2D simulation. This is 3D. But what they did was they took this model and actually applied it to 1,540 population 3 stars. This is some heroic work done by Shigeru Rano now 4 years ago, where they applied it to 1,500 of these cases because they're interested in what is the IMF of the population 3 stars. So they took this big, not big, but they took the cosmological volume, that was 3 megaparsecs over H across, and did these types of calculations. And what they found was that you still get massive star formation, right? The mass spectrum is still top heavy, where the typical, so just look at the total one. I wouldn't pay any attention to this bimodal distribution, but the typical masses are around 100 solar masses. You don't see any halos just forming like a few solar masses of stars here. Because why is this important? Like, why is everyone trying to look for the population 3 star IMF? It's because, right, we need to know the IMF to know the next step toward the first galaxies. If we lay an IMF over the stellar endpoint, so this is a graph by Alex Hagar, and this is showing the stellar endpoints as a function of the initial mass of the star. And also, this is metallicity, the y-axis, so just focus on the very bottom, metal-free. So we have regular type 2 supernova from like 8 to 40 solar masses. You have collapsars going directly into black holes, roughly, these are non-rotating models, this is pretty old, this is like 2003, from 40 to around 100 solar masses, or 140, and compared to Billy supernova, or special supernovae, from more mass of 140 to 260, and more collapsars at higher masses, right? But given an IMF, then you get a percentage of seed black holes that you could have. They could grow into larger black holes. and some fraction of the stars that enrich the pre-galactic material that then go on to form the first galaxies. That's what we need to go to the next step, galaxies. Oops. So I want to show like all of this in action. Let's see. Okay, so I'll let somebody narrate.
How did they get him?
It's awesome. Never got to meet him. So I can only give credit to Donna Cox at NCSA. She directed and produced, and her team produced this movie, and it's a simulation, right?
You should just pay that guy to record your whole talk, and you can just sit and drink.
I know. I don't want to. His voice is so addictive. Yeah, it's like butter. But it's like you know, one thing that you saw from that is that one thing that we include in our simulations is radiation transport. You can see those H2 regions grow with time. And we want to see how that radiation feedback, how that preheating of the pre-galactic material and then chemical enrichment of that material actually affects the first stars. Okay, bringing to my next topic, how do we enrich the pre-galactic material? This is just 2 slides on this one paper by Britton Smith and myself and other collaborators where we looked at 2 stars going off. I'll show a movie after this. 2 populations, 2 stars forming around Redshift 20. They have, so we didn't want to introduce any uncertainties in the IMF, so each one of these stars is 40 solar masses, and they produce, they end their life in a type 2 supernova with 10 to the 51 standard. So, but basically they form, one forms at this halo A right here. You can see it, this is the H2 region very shortly afterwards. There's a supernova going off, and there the metal is going. But what happens is that the supernova is going to enrich, externally enrich this halo here, right, halo B, which has been totally disrupted. And this is one way to actually enrich, start that transition from metal-free stars to metal-enriched stars. So this movie was made by Britton Smith, projected density and projected temperature. So here's this nice timeline here, so you can see we're enriching 30 or so. At the first halo that collapses from the formation of H2, it collapses, forms a population 3 stars, H2 region grows, it lives for 10 million years, and explodes. And you can see it completely disrupted its host halo. Because the halo is 1 million solar masses, its escape velocity is only 3 kilometers per second. You can see all these Rayleigh-Taylor instabilities happening, but it's starting to enrich some of these material there, but before a collapse can happen in that enriched region, this halo collapses, metal-free halo collapses, forms a star, and explodes. You can see the shell fragments a little, but nothing happened. Nothing fragments and becomes self-gravitating, but then it starts filtering in and mixing into this nearby halo here. So it's turbulent, it washes over, and it mixes into this nearby halo, externally enriching it. And it starts to promote its collapse. So this halo itself is only 3 times 10 to the 5 solar masses. So now we're zooming in. So here's a scale bar. We're at a few parsecs across. And here's a metallicity. So it's pretty much like 10 to the minus 5 of solar. It's extremely metal poor. And you can see all this turbulent structure is still monolithically collapsing. So now we're sub-parsec lengths. Use the power of AMR, or I mean any, I guess, Rangian code that can actually follow this inwards. Is now we're at like solar system scale, but at these high densities, we finally start to see fragmentation. That we didn't follow it to star formation, but what we want to see is the thermodynamics and how did the gas actually fragment, and what were the fragment masses, and how is this different from metal-free star formation, and how did the metals actually propagate from its birthplace in the supernova to where the first metal-enriched stars form in this simulation here.
Is that a question for, you mentioned, you have a 40 solar mass, right? And then exploding, and then assuming it has this canonical 1051.
Right.
So how would things change if you were to take a 20 solar mass? Because in terms of observations, we've never seen basically a 40 solar mass make a normal type 2.
Right, so we tried also hypernovae as well, like the 52. We tried, so there are, and it's completely dependent on this, like the explosion energy and the stellar mass, because if you start changing the stellar mass, then the main sequence's luminosity changes as well. Yeah, we also tried, I think, on one recent paper, not written, but I had a paper with Gen Chiake, he used a 13 solar mass star, because I think the abundance pattern of a 13 solar mass star matched with like extremely metal poor stars. Yeah, but it is completely dependent.
I mean, we're just trying to figure this out, what's happening at low metallicities, and how can we map the masses to the types.
Yes.
And so far we only found F2 in the local universe to come from 8 to 16 solar mass.
8 to 16, okay.
There's another problem, the red supergiant problem, but it seems to be on the lower side, and then the higher ones, either other types, or they make kind of supernova at low metallicity, or perhaps there's some discussion that they actually implode.
Wow. Yeah,
Or they're dusty. That's another thing. They're dusty, we don't see them in pre-explosion by HST.
Yeah, for us, for our models, like if we don't do the canonical 10 to 51 and the metal enrichment, we use Kanemoto's models for like the metal masses and the explosion energies. Good update. Okay, so that transitioned us to the first generations of galaxies. So how does that work? We have tens and dozens of population 3 stars. I'll play this over again. So this is the formation of a first generation galaxy, but density, temperature. You can see all of those population 3 stars going off. These are metals from population 3 stars and metals from metal-enriched stars. Over again, but you can see just like cosmic firework going off because they're massive stars. They don't live for long. They're ionizing and recombining all the time. The pre-galactic material provides some pre-enrichment for the IgM that then go on to start forming metal-enriched stars in the central galaxy here. So I think it's important to actually include these population 3 stars because it affects the thermodynamics and how much gas does actually fall into these halos that then go on to form the first galaxies. What are the abundances and what are the metallicities of the stars that form in this ancient mode of star formation? Because if you look at local dwarf galaxies, all local dwarf galaxies have some ancient stellar population. And if we make this connection in between the first galaxies and the ancient population and dwarf galaxies, then we can learn something about these first galaxies without looking across the universe. But you can see that it enriches and ionizes its surrounding regions, and so it's like this is kind of controlling its own fate. But this is a small box. This is from a pretty now old 7-year-old galaxy simulation called Birth of the Galaxy, where we're looking at like 30 galaxies forming and around 300 population 3 stars. But another thing that we did with these simulations is actually looking at the fraction of UV light that comes out of these galaxies, because that's a very important, a very difficult quantity to actually calculate that goes into reionization calculations. But what I'm showing here is the density projections and the UV light projections. And you can see how dynamic this is. So this is the escape fraction. It starts at like 2%, and it goes up to above 10%. So 10% is like, if you're not familiar with this field, 10% is like a value that most people use, but it's time varying for this one galaxy. And it is correlated, and you can make sense of it, it's correlated with the star formation rate. You can see it's still tiny, but it's a tiny galaxy. It's like 0.02 solar masses per year. And this is a halo mass that increases by a factor of 2. It's still like a few times 10 to the 8. You can see just how dynamic it is. Like the ISM of this first galaxy is just turning away as star formation occurs. And it has radiation feedback, has supernova feedback, has chemical enrichment that affects all the cooling and heating of the ISM. And because it's turning away, right, it's a turbulent ISM, and you have all these open channels, it's very porous, and that porosity allows for the ionizing radiation to actually escape into the IGM, contributing to the large-scale ionization of the universe. Yeah.
So when you calculate the UV escape fraction,
Yep.
you take into account extinction by dust, because dust can be formed very fast with the ejectives.
Yeah. So this is an escape fraction above our resolution limit.
Okay.
There are many. I can't take credit for it. Nick Nen says this all the time. Like, depending on your resolution, like there's several escape fractions. There's like escape fraction from like molecular cloud, or even like what you say, like a supernova ejecta, right? But I think at this, I remember it was by Nick. It was like, if there is any absorption above the Lyman limit, right? At 15 eV, for instance, like, do you have any? Does dust actually absorb that much radiation above the Lyman limit? Remember, it was unimportant.
Because it's
Yeah.
UV. So UV is the
Yeah. So this is all ionizing, hydrogen ionizing radiation. Yeah.
John,
Yes.
it seems that the peaks in the escape fraction are correlated but offset in
Yes.
time from the
Yep.
peaks in star formation. Is that because of the fact of the first supernovae then clearing channels and the escape fraction?
That's exactly
goes up?
why. Yeah, and it also takes time for the ionization front to actually make it out of the virial radius.
So the escape fraction is actually, you're measuring that
At the virial
at the
radius.
radius, right?
Yeah,
That's-
the virial radius. Well, it's increasing. It starts out here. Goes out like that. Yep. But yeah, a better paper that I never looked at that correlation, but I'm blank. Tyson Kim. It's K-I-M-M. Him and Renyu Chen, they actually looked at that correlation. Well, but yeah, they're definitely correlated. That, but looking at, we want to make the correlation or make that connection between physical and observable properties of these first galaxies. And all things that we've seen and other groups have seen is they're very clumpy, very irregular, and that's kind of expected for more low mass galaxies. But I found this, I just want to highlight this one result by Ma last year, but I find it super interesting. Depending on your sensitivity, your telescope sensitivity, right? If you have a clumpy galaxy, you have a sensitivity of 25.5 magnitudes per square arc. I'm not a number. I don't think many people are. Or arc second. You see like one clump, right? This is something that you would typically see in very deep fields. But once you start to get more and more sensitive, you can pick up more of these clumpy-like galaxies. I know this is more like what James Webb would actually see. But you can see like the field of view that they're looking at was 2 arcseconds across, right? But this is still a large galaxy, large at that point. This is at redshift. This is how this first. I think it's like redshift 8 or so. And basically they have the same UV magnitude, but there are different stages in their star formation history, right? One's undergoing a burst that has a lower star formation, or lower stellar mass, and one's more massive, but in some quiescent phase. But yeah, given the same magnitude, they may be at different phases, and it's important to actually look at their morphologies. Okay, so now I want to highlight, spend like the next 15-20 minutes on some results from the Renaissance simulations. where we put all of this together, what we learned about from the first stars and the birth of galaxy simulations that we ran before these large simulations and spent a lot of time on. Okay, so these, or a large simulation box, are for us, so a 40 co-moving megaparsec across. We did, in this large volume, looked at 3 large-scale regions. Some bias region, or a rare peak that we call it an overdense region, a mean region that was like the form of Milky Way, and a void region. So we ran it for computational regions to different redshifts, just because, given a certain amount of, like an overdense region would form more stars, so it require more work per physical time. So we can't run it for so long. But at the time, it was very highly resolved. Now people have finally, more and more higher resolution simulations have been run, but at the time it was pretty high resolution at 30 solar masses, 1,000 solar masses for dark matter, and so we can resolve most many halos above a million solar masses. And our maximal spatial resolution was around a few physical parsecs. And we included, just like before, populations of 3 stars in this transition to metal-enriched stars, and included radiation transport. And just to give you a sense of numbers, we followed over 10,000 population of 3 stars and 800 young galaxies. So we had 3 of these runs. Each run took like 10 million core hours, 9 months in real time. I ran one of them. That was very painful. The story is I ran one when I was actually still a postdoc, and then it became faculty. I couldn't do it anymore because I don't have time. I just sat there for a year, and then we hired a postdoc. So house shoot right there. But each one was 100 terabytes, right? So this was back 6 years ago, 100 terabytes per run, so 300 terabytes, and that was very big data. It was very hard. It was very appropriate for it. I've tried this before, but now I'm okay. So, right, this is like the whole box. This is a rare peak. This would actually form a 10 to the 11 solar mass halo at redshift 6. This would form a Milky Way-like galaxy at redshift 0, and the most underdense region in the whole box is there, void. We're gonna fly through this region. I think we have sound. No. So first, we're gonna look at a ball that's going to be kind of similar to the one that we saw earlier, where now we're going through all the population 3 stars forming. So now what we're seeing is blue is neutral gas, red is ionized, white is, now we show the ionizing gas, and green is our metals. So you can see all of these population 3 stars going up, ionizing and enriching their surrounding regions, and we get some galaxies forming that have extended periods of ionizing radiation being released, like here. You get more and more, larger and larger galaxies forming. So it starts at redshift of 25. This visualization goes to redshift of 12. There's one big supernova that was close by, close to the camera. So yeah, and now this is static in time at redshift of 12, just flying through this material. And this again was done by the advanced visualization laboratory at NCSA led by Donna Cox. But how they did this, I love how they introduced all the grids in between, how they transition in between. But here's the neutral hydrogen density, the radiation in white, and all the stars. You see all the galaxies that are in here. The ionized gas from radiation and supernova. Yeah, it's just it's where it becomes black magic. How do you actually compose? For me, it's a camera path. That it takes so much iteration to actually make a nice camera path. Also, metals that come out from both population 3 stars and metal-enriched stars. But here you can put it all together and beautifully see what's going on in the universe and in the state of the early universe when it's only 500 or 450 million years old. And now even this galaxy here, this has around 10 to the 7 solar masses of stars, but you can still see these satellite galaxies that only have 10 to the 4, 10 to the 5 solar masses of stars. So even back then, you have these tiny galaxies that probably would, in this case, they'll come and merge later on, but you can imagine a fraction of those that aren't so clustered would survive until the present day and be isolated dwarf galaxies. But what's the easiest thing to do with these large data is to count galaxies. And this is one of the first things that we did was to actually calculate or to compute the luminosity function And what I show here is only that normal region, that movie that we just saw at different times. So here is the extrapolation from Richard Bouins and his paper from 2015 at Richard 12. It's just a steep low mass power law, but I mean, in a sense, it has to turn over. It can't keep on going. So, because then it would start to diverge, but you wouldn't expect all the halos to form some galaxy. It has to turn over at some point. And we started to actually see that. So here's at redshift 18, 16, 14, and 12. But we saw the deviation from this power law at like a magnitude, UV magnitude of 1600 angstroms at around -14. So the reason for this is because this is when star formation becomes inefficient, just because it can't cool and it can't retain gas within its potential well. Because you can get this bursty star formation, but at any lower mass halos, you start to lose gas and can't continuously form stars. So you can imagine, you can do a simple exercise, you can have one stellar cluster forming, say, 10 to the 4 solar masses of stars, right? That's some small stellar cluster that would have an absolute magnitude of around -10, -12 or so, right? But because it's embedded in that shallower potential well, it'll blow out all the gas, there'll be one burst of star formation, and then it passively ages. So here you would have like one stellar cluster, one young stellar cluster, and then that galaxy would passively age, get dimmer and dimmer with time. And this is how we get these very dim galaxies, which have no hope of being observed at redshifts, very high redshifts, even at like redshift 3, you couldn't observe any of that. So you have the strategy of doing far field cosmology. James Webb would probably see like -14, -12 if they get lucky with the lensing. So you want to constrain the galaxy luminosity function and also the quasar luminosity function in the far field here, but you want to use near field cosmology, right, with the dwarf galaxies around us today to actually constrain the load. And I was explaining this in words, but here are the fraction of halos that contain young stars, young meaning younger than 20 million years. So you can see this transition from almost 0 of the halos containing young stars, just at the atomic cooling limit, which is basically you have to cool through metals or molecular cooling here, and here you can cool by atomic hydrogen. But basically anything below that, you can form some stars, but yeah, I mean, only like a few percent can form stars at a very inefficient rate. But then above this, all the halos form stars, right? And this mass scale is the main reason why you see the deviation from the power law and the flattening of the power law. And actually, I don't like to say it turns over, because this is when it reaches like our resolution limit, right? This is really dim. This is like 1 star particle. I throw that away in the garbage. If you're considering one galaxy as 1 star particle. And also, for these small galaxies, their gas fractions are wildly different, ranging from like gas-free, basically, or very gas-poor, up to the cosmic fraction of megabaryon over megamatter. Depending on these at low mass or low fractions experience very heavy feedback episodes with a lot of population 3 stars going off, blowing out all the gas from radiation feedback and supernova, where others, they may have formed like small amounts of stars or had some time to recover. The thing is, if you start to form stars, here you have a reduced gas fraction. So star formation in these early galaxies will be weaker if you only have like 10% of the gas fraction compared to the cosmic fraction here. Because if you consider star formation in these low mass halos, you would reduce the gas fraction, but if your resolution isn't high enough to actually include these many halos, or your physical model can't include these many halos, you would not have star formation at all, and you'd still be here. And you'd probably overproduce stars in these lowest mass galaxies here, just because you haven't considered any feedback mechanisms at the lowest mass. Okay, I went over that. And yeah, I mentioned near field cosmology, where we have to look at these low mass, we have formed these low mass galaxies, low luminosity galaxies at high redshift, but there's no way we're going to observe those in the next like 20 years. But we can use near field cosmology, and I saw this plot like a few years ago from Kristen Quinn. She showed, I found this amazing, that you look at the Big Bang magnitude of these local dwarf galaxies. Like she took Leo P, for instance. Right? This is the look back time today. It has a magnitude of -10. But over cosmic time, it's pretty constant, depending on like which model you use. So we can take these local dwarf galaxies to actually see what they're doing at ancient times by looking at their color magnitude diagrams and then converting that to stellar star formation history and making that connection between the near and far fields. And this is just for many different galaxies, dwarf galaxies, right? You can see for every one, they don't vary that much over 13.5 billion years. I think that's amazing that they keep on forming some amount of stars over time, and that's represented by these bumps here. Okay, this last 5 minutes or 10 minutes, I want to spend time on how do we form massive black holes. And you can, going back to asking these questions, right? We all know that all galaxies have central black hole, supermassive black holes, but how did they form in the first place? And why did some grow so rapidly? And how common are these supermassive black holes at all times, right? Not just the present day, but how did the M-sigma relationship evolve over time? And I love to show this. I mean, Martin Rees made a great diagram. Also Mitch Big. This is 78, I think the original paper was. But all these are, still feasible, right? We all start from a gas cloud, but we go through many different stages all the way to a massive black hole. And what we've been focused on for the last year or so that culminated in a paper earlier this year was this way, where we're actually going from a gas cloud, it monolithically collapses into a supermassive star, meaning like 1,000 solar masses and above. And then, right, undergoes some instability. We can't follow this GR instability, but once we form like something that will form a supermassive star, a massive black hole could form in these pre-galactic gas clouds. So I was getting ahead of myself, but we want to look at some of the most massive black hole seeds that are forming in the early universe. And this is one volume rendering that I made in my PhD, basically looking at the collapse of one of these atomic cooling halos around 10 to the 8 solar masses that are metal-free. But what you're seeing here, like how do you actually collapse all the way down to very small scales? And you have enough rotation, you start to form bars. You get M=2 bar instability. You get bars within bars, which have been used for a long time for AGN fueling. Here's a second bar that's kind of perpendicular to that first bar, but that's just a way for angular momentum to be transported outwards so that low angular momentum can just flow into the center of the galaxy. And you can see, this is 11 years ago, now we're reaching the limit of our visualization tools back then. Jitter because of machine precision. Yeah, so, but here, like the whole goal is to actually produce a massive seed, so what's known as a DCPH or direct collapse black hole. And to do this, you need very special conditions, and I want to point out it's hypothetical. And I'm still not convinced that they actually form or not, right? Whether a supermassive star actually forms, and we need like future telescopes to actually verify this. Not only James Webb, but also like future X-ray telescopes, like Lynx do it, maybe, yeah, But how do we actually do this? How do you form a supermassive star in the first place and then form a massive black hole? Because number one, you have to avoid fragmentation. Because if you have fragmentation, you'll just form a dense stellar cluster, like a collaborative cluster, for instance, which we don't know form yet. But basically, if you want to avoid fragmentation, you have to keep warm to keep the gene's mass high. Right? We want something to form on that order of magnitude. So to keep it warm, we have to suppress cooling. We have to keep it metal-free, so it can't cool by metal cooling lines, and we have to keep it relatively free of molecules, or H2. Right? That's the first condition. And second, to actually grow these supermassive stars, you have to have very high accretion rates. And from the stellar models that other people have done, you need accretion rates above like 400ths of a solar mass per year. Right? So to do that, you need a deep potential well, or a very atomic cooling limit. Well, what I show here is this is from Hosokawa. So here is showing the the stellar radius as a function of mass, stellar mass, for different accretion rates. So at some accretion rate here, 10 to the minus 3, you can see as a star grows, it becomes more and more bloated on the Hayashi track, and then it goes to main sequence, and this is where it starts to diffuse hydrogen, and then it grows. But here you can undergo some pulsations, right? It can become like on the Hayashi track, it'll start to try to go onto the main sequence, then undergoes this pulsations here. But if you have a very high accretion rate, it'll never really leave that Hayashi-like track, and it'll always be like a red supergiant, right? Even though it's still a protostar. So this is like one way, so this just sets like what actually happens when you have very extremely high accretion rates onto a single star. Okay, so so we need to be metal free, and we need to be free or relatively free in molecules. You need to suppress cooling. So one idea is we need to be metal free, so we need to be far away from galaxies. So this is just my rendition of we have galaxies, you have metal-rich outflows coming out of those galaxies. But also you need to be molecule field free, so you need to be in a strong radiation field. So you have to be close to a galaxy. So you have to be in this Goldilocks region, in this shell here. You have to be far enough away from the galaxy to be metal free. You have to be close enough to be molecular free here. So Goldilocks region here. So just the right distance away from this galaxy. So that's called the close pair scenario. So we played in this scenario. Many others have, like my grad students Cheng and Eli, and also my collaborator John Reagan and I and others looked at this close pair scenario where you have a galaxy and a nearby halo, in which we didn't really simulate the galaxy. We just said we had a radiation point source here, and we wanted to see how that affected. This is a number density here. We have a halo forming here. We have a radiation point source here. And we wanted to see how this affected the collapse of this nearby halo. So this is temperature and this is density here. And we wanted to see how strong of a radiation field did we actually need to suppress any prior star formation before collapsing into a DCBH or direct collapse. Right, and we found that we need a very strong radiation field of around J of 10 or 100 of J21, which is like around the average of the background of these early times. Right, what we saw in this Nature Astronomy paper is you need a very specialized region, this Goldilocks zone, basically because you can't be too close because you'll be stripped from, or be ram pressure stripped. You can't be too far away because you wouldn't have enough radiation. And you can't be too long after you have that galaxy forming, but if you wait too long, those metal-rich outflows will reach farther and farther, so you can't be forming that DCBH too far in the future after the galaxy actually forms. So you have this really specialized region of synchronized halos forming. But what we found in the past year that came out in Nature in January was that there is another way to form a massive black hole seed. Is that we can actually have a very rapidly growing halo that induces what's called dynamical heating. I did not come up with that. That was Naoki Yoshida back in 2003 applying to population 3 stars. Basically, the whole idea is you have a rapidly accreting halo. You're growing the halo very rapidly, and then you're heating the gas, right? You have some virialization of the gas, you add heat to the gas. But in these mini halos, H2 formation is so inefficient. Right? It's very easy to overcome those cooling rates. So any type of heating, like from virialization, can prevent the cooling from H2. But once you get to atomic cooling halos, those cooling rates go up by orders of magnitude, and this no longer becomes important. But what we found was that we took the Renaissance simulations and searched for halos that were metal-free and atomic cooling, so 10 to the 8 solar masses and above, approximately. We just searched for those. We didn't run the simulation. These simulations had no black holes whatsoever. We didn't run the simulation for that, but 5 years after running it, we searched for these special halos. And we found 10 of them. This is highlighting one of them that formed. And what I'm showing here is its density is in black and white, orange is temperature, and purple is density. And these lines here show the Lyman Werner or the dissociating radiation intensity, so J21. And so before it was thought that you need around 100 or so in J21 of the radiation background, but we found that it was a factor of 30 less here, and it's outside of these galaxies here. But basically what is structure formation that determines whether or not a massive black hole or supermassive star would actually form in this halo here. So we found 10 out of 700 or so atomic cooling halos in this simulation here. And also I got some press from a certain news agency just like 2 miles away from me. That was pretty cool. But here is their mass accretion history, where you have, right, these are 2 halos that we investigated over time, so time is going this way. You can see, so here is the mass accretion history. This is given the radiation background, we can convert that into minimum mass in which forms population 3 stars, and this is the atomic cooling limit. So what happens is you have this halo undergoes some very rapid accretion history here, and this slowly grows. And that's where it starts to collapse and form a supermassive star. So what happens is you have this very rapid accretion event. It actually takes a sound crossing time to virialize. It takes another dynamical time to collapse to a point here. And here, in this other case, we had 2 rapid accretion events here where this kind of prevented this first one. It was trying to equilibrize afterwards, and it couldn't form any population 3 stars here because it was still recovering for this event. And then it underwent some accretion event here, popping it above the atomic cooling limit, and then forming, undergoing a monolith collapse here. So I want to point out that these, in the end, right, they jump from this regime from Pop 3 star formation to a regime where you can actually form these supermassive stars, or above, I'd say, now that looking at more recent work, probably around 1,000 solar masses or so. But I want to point out that they're probably not the seeds of the Sloan redshift 6 quasars, because they are forming far away. So the galaxies are forming here, and they're forming on the outskirts here, like 10 kiloparsecs away. So, but could they be like these faint high redshift quasars? I don't know, but we have to do future studies and just to give you a sense, spatial sense of what's going on. Just rotating around density and temperature, these projections from different angles. So we can zoom in. This is one of the halos that actually, you have a disk forming that's around tens of parsecs across, and it actually fragments. It cools from 10 to the 4 Kelvin to around 1,000 degrees in the disk. So here, there are 3 fragments in this disk. Let's see, 1, 2, 3, and it still cools by molecular hydrogen cooling, and it's still a very turbulent region here. And in these clumps, these fragments that form, you start to get heating inside of this, and this is where we believe that the supermassive stars or very massive stars form. And these clumps have masses around 1,000 solar masses. Okay. So that's the last slide I have, but in summary, I think that the first generations of stars, these population stars, are very important to consider in any type of galaxy simulation that want to focus on the first generations of the first galaxies, right? But the current simulation, they still suggest that you have a top-heavy IMF, and right, they pre-enrich and they preheat the pre-galactic material that then go on to the first galaxies. And we see, I didn't talk about this much, but there are 2 types of enrichment in which, if you have the fallback of the supernova onto the sun's halo, you can have a metallicity, this produces metallicity floors of 10 to the -3, or if you have incomplete mixing, which I did show in that one movie, into a nearby halo, you can have extremely metal poor stars. These first generations of galaxies, they're very dim. They're most likely very dim. They're clumpy. One thing I think is important to look at is also the morphology, which I showed by Ma's work. Also, the sizes are important because that goes into lensing considerations. But I think the number one thing to take away is the luminosity function. It flattens just because you have this transition from efficient to inefficient star formation. And lastly, I just went over like how do some of these first massive black holes form? And now we discovered a new pathway to forming these massive black holes, and they may form in rapidly growing dark matter halos. And that's it, and I thank you for your attention.